All right, welcome back. This is part three, I guess, or part two of our topic four, discrete probability distributions. We will talk about the second kind of probability distribution of DPD, which is the binomial distribution. So even before we get to binomial distributions, we should talk about what a binomial distribution even means, right? How you are able to classify these distributions is through what we call repeated Bernoulli trials. A Bernoulli trial is basically a repeated trial whose outcomes are independent of one another, right? So number one, the experiment consists of n repeated trials. So say for example, excuse me, you have five things that you want to do, and each of them have the same kinds of probability of success or failure. Number two, for each trial, there are only two mutually exclusive outcomes. Note these words, two mutually exclusive outcomes. So if one does not happen, the other must happen. If the other does not happen, the one must happen, right? So success and failure. The event that corresponds to success is chosen arbitrarily. What do we mean by this? Well, basically, tayo ang bahala. Right? In essence, what a success is does not have to ascribe to something that is positive. Usually, a success in many cases refers to something bad that has happened. Say, for example, if something is defective, it's a success because that's what we want to analyze. Usually, it is defined in accordance to what is required in the problem. See, that's what we say. And now, if the probabilities of success and failure are denoted by the letters P and Q, that means that P plus Q must be equal to 1. Right? So say for example, in flipping a coin, or rather, say for example, I don't know, in tossing a die, say for example, the outcome that you want is a 1. So that means the success is rolling a 1. And a failure is rolling anything besides a 1. That means that the success rate is 1/6 and everything else is 5/6. Right? And number three, the probability of success remains constant from trial to trial. This is what makes it a Bernoulli trial. And this is very important because the hypergeometric distribution, the next one that we'll talk about after the Bernoulli or the binomial distribution, it just has this change, right? The probability of success in a binomial distribution is independent of the trials, right? They are not affected. The repeated trials are independent. Or if you want to think about it, say for example, you're going to pick, I don't know, a ball inside a ball pit, and this ball pit has many balls. The thing about it is once you pick a ball, you will put it back in again, or it is with replacement. Okay? It is with replacement. These binomial distributions are with replacement. This means that the outcomes on any given trial does not affect the outcomes of the succeeding trials, right? So if, say, for example, you won, quote unquote, you won trial one, it does not matter that you're going to win again in trial two. It's not like because you win, the probabilities have changed. It's not like you lose, the probabilities have changed. No. Each trial is independent of one another. And that is why I suppose we should make it very clear because, well, many things could masquerade as the binomial distribution. So let's be clear, if it checks these three, right? If it checks these three characteristics, then it is a binomial distribution. Now, we can write down the binomial distribution in our little formula sheet right here. We can go here and we can write down the binomial distribution. Binomial distribution in this case now has to do with a PMF. How did we write this before? A PMF here. PMF here, which is going to be, what did I use? P of K. The probability of K successes happening is going to be N choose K times P, right? The probability of success raised to K times 1 minus P, the probability of failure raised to N minus K. This is for K is equal to 0, 1, all the way to N. Okay? This means that your possible Ks have to equal, or rather the different possible outcomes have to equal the possible values of k. You can get no success at all, right? Oops. You can get no success at all. Yeah, there you go. No success at all, or all of your trials are successes, right? All success. And now, in this case, you can also put in here your mu, which is going to be very easy to remember. It's just n times p, the number of trials times the probability. And then your sigma squared, your variance is going to be n times p times 1 minus p. And so now, this might seem very daunting, right? And it might seem like you are just going to, you know, you're just going to memorize this kind of equation right here. That's okay with me, but I do recommend trying to understand everything first. Say, for example, we'll just have a little tiny example in here about, well, coin tosses. Coin tosses, in this case, are going to be what? Right? If you remember the first time when we were talking about the different coin tosses, sorry, coin tosses, when we were talking about those kinds of coin tosses, right? I made up a distribution, what do you call this? A distribution, a probability distribution of my own, which was not correct, but you'll see it is kind of correct. Sometimes it's not, sometimes it is. But in this case, say for example, if we were to flip a coin, right? If we were to flip a coin 3 times, right? What would happen in here is that the number of our trials, letter N, right here would be 3, right? Trials. And then in this case, the K denotes the number of our successes, right? And again, success in here does not mean something positive. It just means whatever it is we want to study. The probability of success is letter P. Probability of success is letter P. And there you go. What this basically means is something like this. Say, for example, we have 3 trials, and the probability of success, say, for example, is the probability of getting heads, 0.5. Of course, it's just 1/2. Right? And this means that your binomial distribution, because a coin toss, right, the results of the previous coin toss should not influence the next trial's coin toss. I don't understand why I get confused there. Should be 3 choose k times 0.5 raised to k times 1 minus 0.5 raised to 3 minus k. It just so happens that 1 minus 0.5 is also 0.5. So what we can do is we can add these together, actually. 3k and then 0.5 raised to k, and then 0.5 raised to 3 minus k. Would you look at that? You can actually add these together, right? 0.5 times raised to k plus 3 minus k. You can cancel the k's. You will get 0.5 raised to 3, which is indeed 1 over 8. So actually, right, the binomial, the probability distribution that I thought of earlier, right, this one is actually correct, right? But not in the way that you would expect it to be, okay? But now let's just go ahead with the next kind of explanation. For the explanation, what's going to happen now is that, well, we'll have to break these things down, okay? We'll have to break these things down in the sense of, well, you're going to have to think first of this little box right here. This box contains n choose k. Out of the trials, you're going to choose how many successes there are. Okay, so that basically brings up all of the possible outcomes in the sample space. Say, for example, I don't know, the sample space for 3 coin tosses would be 8. And out of those 8, right, 3 choose, I don't know, 1 would reference how many of those outcomes, right, have 1 head. In that case, that would be 3. So in this case, that would mean that that is the number of, or rather, that is your multiplier, right? It's telling you, okay, there are 3 times that this has happened. That what has happened, right? What is the probability of those successes happening? Well, Again, for this binomial distribution, all of your probabilities are independent. So in this case, right, these things are independent of one another. If you succeed, that is towards this count right here. If you fail, it's towards this count right here. Notice that what happens basically is that in a coin toss, right, you start with the first round. In a coin toss, you have an equal chance, aka a 0.5 chance of either a head or a tail happening. Maybe let's think about this in terms of a die throw, right? In the first round, if you want to get a 1, right, versus if you want to get a not 1, this has a 1 in 6 chance. Meanwhile, the failure has a 5 in 6 chance. Say, for example, you roll again, right? You roll again, and then, right, there are two possibilities again of you getting a 1 and of you not getting a 1. In this case, you have a probability of getting 1 and then a probability of not getting a 1. And in this case, you have 1/6, 1/6, 5/6, and 5/6. Right? Note that in these cases, right, how do you get to answer how probable this outcome is? Well, I would have to say that this is only one outcome. There's only one outcome where I have selected two, or rather where the results are, both of them are not 1. And both of them have a probability, or rather this outcome has a probability of 5/6 times 5/6 happening. If you want to get, right, an outcome where there is only one time you've selected or rolled a 1, there are two outcomes. In this case, 1 and then 2. And then both of them have a probability of happening of 1/6 times 5/6. And because there are two of them, you're going to have to multiply by 2. And then if we just round out this we round out this explanation, there's only one outcome where you roll ones every single time. And that has a probability of 1/6 times 1/6. This formula right here of the binomial distribution basically generalizes all of this. What this says is that, well, this is n choose k. This tells you the multiplier, right? How many outcomes are possible. And this part right here tells you the probability of each outcome happening at the same time. Because they are mutually exclusive and only one, right? And only one is happening or the other, right? You can denote the probability of success and the probability of failure. And because each trial is independent of one another, you can just multiply them, right? You can just multiply them. That is your binomial distribution. Okay? All right. In this case, I've explained basically what they're saying in here, right? The mean of X successes is interestingly 100 times P% for all of the N trials. So say for example nga, right? What is the expected value of you getting, I don't know, a 1? Well, it's just 1 times 1/6, right? And then everything else does not have value. So in this case, you're going to have to repeat the number of trials times the probability of success. So say for example, right? Say for example, you have again 3 coin tosses and you have probability of success is 0.5 because it's a coin toss. The probability, or rather the expected value, is going to be 3 times 1.5 0.5 excuse me, or 1.5. What this means is that you're going to get heads roughly 1.5 times, which kind of makes sense, right? Which kind of makes sense because it's just half of every single time. That's what you expect to get. Okay? Let's do a simple example now. In the last civil engineering licensure exam, the LSU was noted to have a passing rate of 59.26%. Suppose we have 20 examinees in the coming licensure exam this year. Let C be the number of students who will pass this year. What are the probabilities that everyone will pass and at least one student will pass? So in this case, this is going to be slide 21. Slide 21, let's try this out. They say that our probability of success of this thing happening is 0.5926. This is the passing rate now of students. And because there are 20 students, we can check that that is a binomial distribution, 20. Now, in truth, this is really not a binomial distribution, especially if, say, for example, these students are going to review together, or maybe they're friends, they want to, I don't know, see each other succeed. So if one succeeds, then probably the probability, right, of the other succeeding is going to change, right? Or, well, my point in here is that the probabilities are not independent. Most probably the probabilities are not independent, but in this case, we're talking about the binomial distribution, and we want to keep this very parang simple. So let's just treat each student's probability of success to be independent from one another. Okay? What are the probabilities that everyone will pass and that at least one student will pass? So, ang pinapatanong sa atin, letter A, what is the probability that all 20 will pass? And letter B, what is the probability that at least one student will pass? Say, for example, this thing. Okay? The first one, it's very easy because we can just plug it into our equation. F20, right? Because there are 20 successes, let's make this yellow. Right? N equals 20. We now know that it is going to be 20 out of 20 students, choose 20 successes, aka all of them are going to pass. They have a passing rate of 0.5926, and that makes them 20. And then the failure rate is just 1 minus this value, which is 4074, raised to 20 minus 20. Note that I am color coding in here because, well, there are two values of 20 that may confuse a lot of you, right? And we can get in here that 20 choose 20. Actually, if you guys want, there are shortcuts to this so that you don't have to put them in your calculation. If you see an n choose n, right? If you see an n choose n, that is basically n factorial all over n minus n factorial times n factorial. N factorial over n factorial, of course, that is 1. And then n minus n is 0 factorial. And 0 factorial gives you 1 as well, which means this is just 1. The same way, if you choose 0 and choose 0, this will still be equal to 1. Okay, there you go. And, right, I suppose even more tips and tricks in here would be, right, even more tips and tricks would be if you were to put in and choose 1, right? And choose 1 would be, will look something like this, right? N factorial all over n minus 1 factorial, and then times 1 factorial. 1 factorial, of course, is just 1. And then n over n minus 1 factorial, or rather n factorial over n minus 1 factorial is basically the same thing as, right, n times n minus 1 factorial all over n minus 1 factorial. So in this case, they can cancel, and you will be left with n. If ever you see n choose 1, you don't have to pick that anymore. Just go with n. The same goes for n choose n minus 1. N choose n minus 1. So notice what happens in here is that there is a kind of symmetry. If you choose either everything or nothing, there is only one possible outcome for that. If you, from n, you choose only 1, or from n you choose only n minus 1, they have the same factor. Okay, so that's it. And from here, I can immediately put this as just 1. And I don't have to put that many things into my calculator. Look at this as well. 20 minus 20 gives you 0. Anything raised to 0 is just 1 as well. So I really just have to put 0.5926 raised to 20, which gives me this very small number, 0.0000285 or 029. Right? So this is a very small value. In my calculator, it read as 2.85 times 10 raised to negative 5. So 1, 2, 3, 4, 5. That is 2.85 times 10 raised to negative 5. Needless to say, this is a very small probability. And hopefully, it makes sense to you guys that this is almost impossible. All of them passing all together will be very impossible, because if you think about it, it's only a 60% chance that one student will pass. How many times does it have to take, right? How many times does it have to take? Say for example, if you still can't wrap this around your head, right? 60%, you will win 60% of the time. Someone very unfortunate is bound to fail because it's not 100%. Right? Especially because this is 60%, that's like 3 out of 5. So it's almost guaranteeing as if, right, out of 5 students, only 3 will pass. In this case, we can go even further. We can think about the expected value. How many students do we expect to, right? How many students do we expect to pass in the first place? In this case, 20 trials, 20 students times 0.5926. This will give us a value of 11.85. So they say that in this case, about 11.85, or maybe if we want to push our luck, maybe 12 students are expected to pass. Of course, if we get 13, then that's cool, right? That's very fortunate. If we get 14, even better, so on and so forth. But as you go higher or as you go lower, it becomes more improbable. We're just saying that on average, there will be about 12 students who will pass. Now, letter B, at least one student will pass. Now, any kind of probability student will be very happy to hear the words or to hear the phrase at least one. Why is that very important? It's because we can now invoke the complement rule. If you guys remember what the complement rule says, it's basically the probability of something happening is 1 minus the probability of it not happening, right? In this case, the probability that at least one student will pass, right? Or your random variable C is going to be bigger than 0, at least one student will pass, right? Will be 1 minus the probability that no student will pass. Note that because I'm writing down C equals 0 because the number of outcomes, the number of successes can only go from 0, aka no success, to n, which is all successes. So in this case, I am just, instead of going to compute the probability that 1 will pass, plus the probability that 2 will pass, plus the probability that 3 and 4 and 5 and so on will pass, what I can do is just choose this, right? This root instead, and we will get 1 minus the probability that nobody will pass. So from the 20, I will choose nobody. And then 0.5269 ba yun? Tama ba? 5926. 0.5926 will pass. 0.4074 20 minus 0 will pass. Note that in this case, 20 choose 0 is just 1. Anything raised to 0 is just 1. So I will just put this value into my calculator. 1 minus 0.4074 raised to 20 will give me like this: 0.99999841. This is almost guaranteed, right? This is almost 100%, no matter how you look at it, right? This is almost 100%, which means that it is almost guaranteed that somebody will pass. If no one passes in these 20 students, then it will be very, very improbable, right? This is actually how I remember how some Minecraft player was proven, not proven like not proven mathematically, but proven probabilistically that he has been cheating. Right? It's because the way, or rather the probabilities don't match up in his favor, right? How he has gotten items, how he has gotten things to spawn has been so uncommon, right? That well, it seems that the kinds of things he does seems to always be so improbable. I'm talking about Dream. right? If you know that guy. Okay, so there you go. That is our computation. There it is. So what they did in here was at least one student will pass. Okay, now let's do another example. Two lighting systems are being proposed for an employee work area. One requires 50 bulbs, each having a probability 0.05 or 5% of burning out within a month's time. The second has 100 bulbs, each with a 0.02 or 2% chance of a burnout within a month's time. Whichever system is installed will be inspected once a month for the purpose of replacing burned out bulbs. So it would be not in the company's best interests to replace burned out bulbs. If we compare the probabilities that each will require at least one bulb to be replaced each month, which system is more likely to require less maintenance? Let's be very clear with the wording here. Which system is more likely to require less maintenance? So if you want to think about it another way, which system is less likely to require maintenance at all? Right? So that is what we want to find out. In this case, this is now slide 20. Wait, slide 20. Where are we? Slide 22. Slide 22. Okay. Slide 22, we have two different systems. The first system, I will denote that with the first N1. We have 50 bulbs with a probability of success as 0.05. You might think to yourself, why would I get the probability of success to be the probability of burnout? Again, the thing here is that success it does not need to be ascribed to any positive value. Just because something, or say for example, just because this bulb has burned out does not mean it is a failure. If you want to understand the number of burnouts, then the successes should be when they burn out. On the other hand, we have another system, N2, which is 100 bulbs, which has a lower probability of burnout. So notice that in this case, right? In this case, the first, right, has fewer bulbs, but each bulb has characteristically more risk. Right? It's more risky as to burning out. But the second one, the trade-off now is that okay, we will lower, right? The light bulbs have a lower chance of burning out, but we will use more of them, right? Just a quick, right? Just a quick expected value would give us a clue of what to answer. Say, for example, what is the expected number of light bulbs to go out for the first system? 50 times 0.5, 0.05 would give us something like, let me just put this in, about 2.5. 2.5 bulbs will go out in 1 month. On the other hand, for here, we will have 100 bulbs, and 0.02, you will have 2 bulbs. So right now, even without thinking about the probabilities, I'm just betting, I'm putting my money on, since we're already in the topic of probabilities, right? I'm quote unquote, right, putting my money on system 2. I think because it will, on average, need 2 bulbs to be replaced per month, I think that might require less maintenance, but we're not sure, right? And so let's just think about this, right? The probability of replacing at least one bulb in the first system will be something like this, right? Say for example, the number of bulbs is in here, wala bang, okay, there's no random variable, so let's just say x1, right? X1 is at least 1, right? At least 1. We can again invoke the law of inverses, right? Which means we just have to compute for the probability of it not happening at all. So in this case, we have 50, right? We have 50 bulbs. There are no successes, right? There are no successes. And in this case, right, we will have 0.05 raised to 0 times 0.95 raised to 50 minus 0. Why are we computing this? It's because whichever system is installed, right, once a month, will be inspected once a month for the purpose of replacing burnout bulbs. If we compare the probabilities that each will require at least one, ayun na nga, right? They made it very clear what kind of comparison we should do. And so this is the kind of comparison we should do. 50 choose 0, 1. 0.05 raised to 0 is 1. We will have 1 minus 0.95 raised to 50, which is 0.923055. 92305. It is 92%. There's a 92% chance of this not requiring, of there's a 92.3 percent chance of it requiring maintenance. On the side of x2, right, it is just going to be, again, via the law of inverses, 1 minus the probability that no maintenance will be done, 1 minus 100 trials, none of them are successes, 0.02, 0.98 is 100 minus 0. We will cancel and then cancel this as well. We will get a probability of 0.86738. 0.86738. Note, which one is the system we want to, which system is the one we want to adopt? In this case, we want a system that is less likely to require maintenance. In this case, we want a system that is less likely for something to break. Less likely for something to break. Therefore, it is correct that on average, or rather, we will only have a 86% chance or an 87% chance of us needing maintenance in a month. It's still high, of course, but it's not as high as 92.3% based on the other system, based on the first system. So that is our answer in here. There you go. That is our probability. They used A and B for their random variables. We used x1 and x2. And in this case, they got the same values that we did. So that means the second system doesn't need as much maintenance, or rather, it will be less likely to require maintenance compared to the first system. That is how we think of these things. Okay, now we go to examples. If you guys want, you can skip to the next video now. Right? The probability that a certain kind of component will survive a shock test is 3/4. Find the probability that exactly 2 out of the next 4 components will survive. So in this case, out of the next 4 components, those are your numbers of trials. And exactly 2 means that we just want to know the outcome for 2. The probability of this happening, of the probability of success, is 3/4, which means the probability that exactly 2 of the next 4 components will survive will be 4 choose 2 times 0.75 raised to 2 times 0.25, the probability of failure, raised to 4 minus 2. 4 choose 2 in this case is 6? I don't know. 4 choose 2 times 0.75 squared times 0.25 raised to 4 minus 2, which is still squared, will give us 0.2109375. There's a 21.09 chance that exactly 2 out of the next 4 components tested will survive. Okay. All right, there you go. And then we have another example in here. The probability that a patient recovers from a rare blood disease is 0.4, 40%. If 15 people, right, are known to have contracted this disease, so this means this is our probability of success. 15 people means that is our N. What is the probability that at least 10 survive? So in this case, the probability that at least 10 survive, X is greater than or equal to 10. From 3 to 8 will survive. Probability from 3 to 8. In this case, I will assume this is inclusive, which means 3 and 8 are both counted, and that exactly 5 survive. We also need to find here the mean and the variance, which in this case is quite easy enough to understand. We have 15 trials and we have 0.4 chance of success, which means that on average, we will expect 6 people to survive. For the variance now, we have 15 times 0.4 times 0.6, which means that in this case, 3.6 people squared, I guess, is our variance, right? So this is our mean and our variance. And sadly, for A and for B, it's going to be quite tedious. It's going to be quite labor intensive. Okay. So in this case, oops, sorry. So in this case, right, let's just write this down right here. What slide number is this? This is slide number 26. Put in here slide number 26. Let's import all of the stuff we know. We know 15 people got the disease. Well, 0.4 is our success. We need the probability that at least 10 survive, the probability that 3 to 8 people will survive, and then the probability that exactly 5 survive. Let's see. We've already solved the mean and variance, so that should be no big deal. In this case, sadly, there is no other way to do it. We need to take into account the probability that 10 survive, 11, 12, 13, 14, and 15. In this case, 15, choose 10, case 0.4 raised to 10, 0.6 raised to 15 minus 10, right? And then 15, choose 11, and we keep on going, so on, so forth. And well, even if I don't tell you guys the answer to this, hopefully you understand what I am doing. Up until 15, choose 15, 0.4 raised to 15, 0.6 raised to 15 minus 0. In this case, we can cancel this. We can cancel this well, and we can try to put all of these together, right? 15, choose 11. Oops. 15, choose 11. 10 times 0.4 raised to 10 times 0.6 raised to 5. Okay. I'll have that, and I'll add that to 15, choose 11 times 0.4 raised to 11 plus 0.6 raised to 4. And then I'll add that to 15, choose 12. Yeah, I'm going to be here a while. 0.4 raised to 12, 0.6 raised to 3. And we keep going. Plus 15, choose 13, right, times 4.4 raised to 13 times 0.6 squared. And then plus 15, choose 14. We know 15, choose 14 is just 15 times 0.4 raised to 14 times 0.6. And then, of course, there's only one left, 0.4 raised to 15. We will have probability of only, sadly, only 0.03, 38, and then 33. So there's only a 3.4% chance of more than 10 people surviving, which is quite sad. But at the same time, we recognize that, well, on average, 6 people will survive, which is good, I guess, right? Now, we repeat the same thing in here. 15, choose 3. 0.4 raised to 3. At 0.6 raised to 15 minus 3. And then plus 15, choose 4. Then 0.4 raised to 4. Then 0.6 raised to 15 minus 4. And then plus all the way to 15, choose 8. Right? All, times 0.4 raised to 8 times 0.6 raised to 15 minus 8. You guys, I believe you can do this yourselves, right? And then lastly, x is equal to 5 is quite easy because now finally it's only one thing, 0.4 raised to 5 times 0.6 raised to 15 minus 5. 15, choose 5. Oops, 15, choose 5 times 0.4 raised to 5 times 0.6 raised to 15 minus 5 is 10. We will have our answer in here of about 18%. 185938. There you go. There's about an 18.5% chance of exactly 5 people surviving. It's not probable, but at the very least, it's more probable than more than 10 people surviving. Or sorry, at least 10 people surviving. Okay? That is your slide 26. Now, for the last example in here, we will have a a multi-part question. We will have a large chain retailer purchases a certain kind of electronic device from a manufacturer. The manufacturer indicates that the defective rate of the device is 3%. So I suppose we should try and put this all here already. 27. Okay. The probability of this happening now is 0.03. I'll treat defects as my success. The inspector of the retailer randomly picks 20 items from a shipment and equals 20. Right? And then what is the probability that there will be at least one defective item among these 20? Let's start solving these first. At least one out of the 20. And of course, because of the words at least one, again, we're very happy. We can just invoke the law of inverses. We'll just have to do this. In this case, 1 minus 20, choose 0. And then you will have 0.03 raised to 0 times 0.97 raised to 20 minus 0, which is just 20. This cancels. This is 1. This is also 1. And therefore, the probability of this happening is 1 minus 0.97 raised to 20, which is 0.456206. 0.456206. This is the probability of at least one being defective. Okay, now we go to the one that is highlighted. Suppose that the retailer receives 10 shipments in a month, right? 20 items from a shipment. So that means that this retailer receives 200 items. But that doesn't matter because we'll look at just the second part. Suppose that the retailer receives 10 shipments in a month and then the inspector randomly tests 20 devices per shipment, right? So basically, this is the same thing that they do in here. What is the probability that there will be 3 shipments containing at least one defective device? So you might say, oh my goodness, there's a lot of numbers happening in here. But essentially, what we have computed right here is a probability of success. In this case, this yellow box in here corresponds to the probability that, right, at least one has a defect. At least one out of the 20 devices, right, is defective. And that exactly fits, right, the description for part 2. That is the kind of probability of success we want to understand. So in this case now, the probability of a shipment containing at least one defective device, your P, your second P, right? If you want to say P prime, go ahead. It's now 0.4562. And now instead of 20 items from a shipment, we inspect per shipment. In this case now, it's 10 shipments. And so for this letter B, we want to say now, what is the probability that 3, right? 3, exactly 3, that there will be 3 shipments, right? Exactly 3 shipments that have at least one defective device. So in this case, we are now changing our parameters. Instead of 20, we use 10 shipments. Instead of at least one, which makes our successes 0, in this case, we need 3 of these hits to happen. And we have 0.456206 raised to 3. And then times 0.543794 raised to 10 minus 3, which is 7. I'm going to multiply all of these. 10, choose 3, times point blah 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 raised to 3 times 1 minus our probability raised to 7. In this case, our answer here is 16%. 0.160216. that is the probability that exactly three, right, that exactly three shipments will have at least one defective device. This makes sense as a two-part question because, well, you need to solve the first part first before you get to the second one. Okay, that is our binomial distribution. Right? We will have even more examples near the end, but those are the examples for the binomial distribution. We will then talk about the hypergeometric distribution and how that's different. For now, I'll see you in the next video. Thank you very much.